Hi everyone, introducing to you an AI-powered system for real-time conversion between English text, American Sign Language fingerspelling, and American English speech from Computer Science Department, School of Computer Science, Bina Nusantara University, Jakarta, Indonesia, with the authors of Dylan Y. Sunarto, Immanuel Sinaga, Felix N. Lim, Setiawan Jody, and Irene A. Iswanto. With the outline, with number one, background, continuing with methodology, reference, goal, and differentiators, system architecture, implementation, results and performance, system limitations, and conclusion. First of all, we're going to go with the background. Well, we think that deaf does not equal cannot communicate. For the deaf community, sign language is a one way they communicate. However, understanding of sign language is very limited. Deaf people naturally can't pronounce because they cannot hear people or talk and cannot hear their own words when they speak, making them able to speak but can't talk well. But the disadvantage of them not being able to talk well doesn't stop them to communicate with other people. Turning into our methodology, well, we're using ResNet 50 based deep neural network architecture for the classifying fingerspelled words and achieving a 99.03% accuracy. And using the American Sign Language hand gesture datasets with utilizing a 7-layer convolutional neural network, or we call it CNN, trained on the ASL alphabet database, consisting of 27 categories with 3,000 images each, totaling of 87,000 hand gestures, image size at 200 times 200 pixels. We also taking advantage of some pre-trained models alongside their respective frameworks. For text processing, we use a few models as a T5, a transformer-based model that frames all NLP tasks as text-to-text. GPT-3, large-scale autoaggressiveness, language models capable of generating human-like text, and sec-to-sec traditional encoder-decoder architecture for text like machine learning translation and summarization. We also use Whisper for speech-to-text, a robust ASR model trained on diverse multilingual datasets, and Wave2Fact, a self-supervised speech model that improves accuracy with less labeled data. On text-to-speech, we use Tacotron 2, a deep learning-based text-to-speech model with realistic prosody and intonation, and a fast speech faster. More efficiency alternative to Tacotron for visual ASL recognition or American Sign Language recognition, we use CNN-based ResNet and also deep CNN-based architecture for feature extraction and MobileNet, a lightweight CNN optimized for mobile, an edge device, as well as vision transformer-based image models for gesture recognition. And our key results are resulting at 96% at the American Sign Language recognition accuracy and also 99% at individual CNN performance.
Referencing previous studies, multiple methods for sign language recognition have already been found. Deep learning approach as a solution has also been gaining popularity in sign language recognition. For example, in some projects, researchers have utilized CNN or convolutional neural networks to classify 20 Italian gestures with high accuracy. And so do Carney and Aldil on their deep learning approach for the sign language recognition. It has resulted in real-time hand sign language recognition models for alphabetical letters using a deep learning approach. 15 to 16% of the world's population has some form of communication disability, and of that 15 to 16% has a hard time hearing. Our goal is to make communications easier, especially for those hard of hearing. What makes our system different is that we are using 3 different core components that includes text-to-speech, speech-to-text, and sign language detector. Combining other research and combining the 3 core components mentioned earlier, the system can facilitate real-time conversion between English text, ASL fingerspelling, and American English speech. The system architecture flows as follows: data input, the pre-processing of the data, extracting the feature of the data, processing with the help of artificial intelligence, and then finally the output result. Core components are text in English, speech synthesis using a generated voice in American English, and then sign language using the standardized American Sign Language or ASL. To improve the diversity of data collection, we include data from multiple sources. Ethical procedures are followed with the data confidentiality being maintained and of course the consent of the sources. As can be seen on the screen, these are the multiple sources of the datasets that we have used alongside the description of what they are. After gathering the data, we must clean the data for optimal results, which resulted in the removal of incomplete, inconsistent, or duplicate data entries. Standardizing the formats of the data will facilitate smoother data analysis, and data validation techniques will also be applied to detect error or discrepancies. There are four main bullet points here: removal of unwanted observations or irrelevant data, fixing structure errors or the formatting of the data, managing the data outliers, and handling the missing data using statistical methods or advanced imputation techniques. Continuing to the preprocessing of the data, which is the next step. The collected and cleaned data will then be pre-processed into more usable formats. Speech data will be standardized for the audio part. ASL data will be segmented for enhanced visual pattern recognition. Excessively noisy, dirty, or unnecessary data will be removed for processing and efficiency improvements. Categorization will be achieved by labeling the ASL data that includes images and videos. For text, the training will include tokenization and encoding of the text data.
Multimodal feature extraction and optimization. Our implementation focus on the three key output modalities to maximize the system accuracy. The first is text processing. For English texts are analyzed to improve observation algorithms and ensure natural language output. And second is speech recognition. Our acoustic feature and extract for speech input, enchant speech to text accuracy, and handle various speaking patterns. The third is ASL recognition, visual feature for finger spelling, gesture, and process using motion tracking to recognize between similarities, sign, and improve gesture recognition accuracy. And the last, system optimization. Statistical analysis determine the most contributing feature for model performance, while feature selection priorities elements that enhance real-time processing efficiency. All extractive features are fine-tuned between on-user feedback to ensure practical usability in real-world scenarios. System limitation. The first is integration challenge. System consistently crash during real-time ISL gesture recognition when all modules are integrated together. Second, technical issue identified. What is the problem and make this is suppressed? The first is memory management, the second is buffering, and the third is task coordination, and the fourth or the last that is real-time performance. And individual component status is ISO recognition, text to speech, speech to text, and integration was crashed when during the system integration, performance resource, and integration challenge. Individual component performance, ISO recognition model are demonstrated in excellent standalone with 96% classification accuracy and integration challenge. We put all parts together, the system crashes and couldn't works in real time. That's the problem. Our limitation, the crash appear to be related to real-time processing and key findings. While each part works great alone, combining them all real time is technically challenging and need more work. Conclusion. We built an AI system to help a deaf and hearing people communicate using ASL recognition, speech to text, and text to speech. What we work, each part performed well individually. Our ASL model got 96% accuracy. What didn't work? The system crashed when we put all together in real time. Why? The memory or processing issue is during integration. The technology works, but we need to fix the integration problems for real-time word use. And let's build the future, breaking the language barriers together. Thank you for watching. Goodbye.